Okay, thank you very much. So yesterday I was a little bit fast in the end, so I will go into the computations. So this was the claim. There is no claim here, but the claim is that if you have for instance, a C1 circle diffeomorphism with the rational rotation number, and if you take these conjugators, Hn, then the sequence of conjugate maps, Hnf, Hn inverse, goes to the rotation in C1 topology. And believe me, this is a totally elementary computation. So I will do the computation, and you will see that there is some algebraic matrix that appears here. So the expression of Hn is totally explicit, but the thing that we will retain is that the logarithm of the derivative of Hn is given by this Birkhoff sum plus some constant that doesn't matter for the sake of computation. So the constant is just the logarithm of the denominator in the first line. So let me go into the computation. So there we have the logarithm of Hn, and now I will compute the logarithm of the dHn, but at the point f of x. And it's the very same expression, 1 over n, the sum of the logarithm of fi at the point f of x. And the only thing that we need to do here is to use the chain rule to write this as the logarithm of the derivative of fi plus 1 of x minus the logarithm of the derivative of f. This is just the chain rule. Okay? And well, there is this constant here, plus Cn. Plus Cn. Okay, and now we do we subtract this from Hn. So we have the logarithm of this minus the logarithm of this, and both expressions are almost the same. Here we have exactly the same sum, except that it is, we change the exponent from I to I plus 1, thank you, Helen. And the constant disappears, and what we get is minus the logarithm of the derivative of f to the power n of x divided by n. And this is a constant that is repeated n times, so this is plus the logarithm of the derivative of f. And in the end, this is very, very nice. So in the end, I will change this expression here. What we are getting is that the logarithm of, so let me write it this way, plus the logarithm of f minus the logarithm of Hn. This is equal to the logarithm of fn to the x divided by n. So this is the equality. Okay? And this is just a chain rule. And now there are two issues here. So the first thing is that this is very nice. This is the logarithm of the conjugate of f evaluated at the point h of n of x. Okay? Again, because of the chain rule. And so if we are able to show that this goes to 0, then this goes to 0 in C0 topology. So this goes to the rotation in C1 topology. Okay? And this is a perfect formula. I mean, there is no approximation here. This is a closed formula. And this is not new. I mean, this is a remark in general in dynamical system. So what we are doing here is that you see this function as a function, and this is you are trying to see this function as a coboundary, okay? And there is a general remark in dynamical systems that if you take a function, then it is cohomologous to its Birkhoff's mean. And this is what is used here, because this is the Birkhoff mean of this function. And they are cohomologous, okay? So this is totally general. Okay, but for this talk, this is a closed formula, and it has a generalization for commuting maps. Okay, so this is the generalization. This is the very same computation, and there is only one point where we use the commutativity. So here the conjugators are means along the composition of two maps, and when you perform the computation, what you do here is changing this expression by some equivalent expression, and here we are using the chain rule, and we are using the fact that f and g commute actually in order to do this computation. And there it is the very same computation. And I want to keep the final output of this computation. So the precise formula here is that the logarithm of the derivative of the composition, say of f, you can do exactly the same for g, is equal to 1 over n, the sum of the logarithm of d fn at the point gj hn inverse of x divided by n. And again, this is an exact formula for the case of two commuting maps. So this is the case where you have two commuting maps and you take hn as the sequence of maps given there. And now the point is that, again, everything is contained, the abstraction in order to perform this conjugacy, in order to show that this conjugates map converts to the rotation in C1 topology is just this one, which is somehow saying that there is a Lyapunov exponent, which is that all the Lyapunov exponent vanish. Okay, so this is the condition that we need in order to conclude that we have the right convergence. And the problem is that there might be parabolic fixed points or parabolic periodic points. And actually there is a very nice lemma, totally general lemma, that says that if you have, for instance, you have one diffeomorphism of the circle or the closed interval, then these two properties are equivalent. The logarithm of the derivative of the iterates of f growth sublinearly is equivalent to the fact that the periodic points of the map are parabolic. So the only abstraction in order to perform this procedure are the parabolic fixed point. Okay, this is a good exercise. I mean, this can be proved by hand. I know that there is an explicit proof for the case of the circle in the thesis of Michel Herman, but this is very natural. If there is some hyperbolicity for the growth of the derivative, then there should be some possible Lyapunov exponent, and this is impossible in dimension 1. So this is very, very simple. For the case of the interval, there is also a very nice proof by Polterovich and Sodin in a very nice paper. They wrote about diffeomorphism of the interval. But again, this can be done by hand. I mean, if the fixed point of a diffeomorphism of the interval are parabolic, then the growth of the derivative is sublinear. Okay? So So in case there are no parabolic fixed point, we are done. So let me discuss a little bit on this, because I like very much the work of the theorem of Polterovich and Sodin. So I will do a little detour on this, and then I will come back to the case of parabolic hyperbolic periodic points. Okay, so actually Polterovich and Sodin proved this as a motivation for a very nice result. So if you take a C2 diffeomorphism of the interval, for which the parabolic fixed points, the fixed points are parabolic, the growth of the derivative is not only sub-exponential. Actually, it is at most quadratic. And this is something very surprising. I mean, it is something typical in dimension 1, so it doesn't hold in higher dimension. So they proved this almost 20 years ago. I am still very surprised of this. And the proof is very nice. So it's a very tricky proof using some kind of Danjois argument and then some lemma, some very tricky lemma about the growth of sequences and so on. So the proof is really very nice. Together with Leonardo Dinamarca, we were able to prove that actually this limit exists. So the growth is exactly quadratic. And one can even give a formula for the growth. So let me give the formula in a simple case. So in a simple case, if you take, suppose that you are in the simplest case. So you have a diffeomorphism of the interval, and suppose it moves everything to the right. So this is very boring. There is no fixed point interior, and you suppose that the endpoints are parabolic fixed point. Then, in this case, the limit of the growth of the derivative divided by, normalized by the square of n, this is equal to 1/2 the second derivative at the repelling fixed point. Okay? This is an exact formula for this growth. And in case there are many fixed points in the interior, you have to compute this value for each of the intervals and to take the supremum of these values along all the fixed intervals. And this supremum is going to be a maximum actually, and this is the limit in this step. And there is something similar for the case of the circle. This was proved by Watanabe also, right after the paper of Polterovich and Sodin. If you take at least C2 plus alpha circle diffeomorphism of a rational rotation number, then the growth of the derivative along iterate is subquadratic. It is never quadratic, actually. It is smaller than quadratic. Okay? So quadratic is something that comes from dimension 1. For our purpose, we only need a sub-exponential growth of the derivatives. So actually, the growth is subquadratic. Okay. So let me come back to the difficult case. So what to do when we have a hyperbolic fixed point? And the idea is a classical one. So we will try to conjugate the map or the commuting maps with these maps of the form x into x to the alpha. These are no longer diffeomorphisms. They fail to be differentiable at the origin. They are differentiable, the derivative equal to 0, okay? So the inverse is not differentiable. But there is a kind of miracle, is that if you conjugate a hyperbolic C1 diffeomorphism by such a germ, you are still C1. And this procedure allows to change the multiplier. So if you start with a multiplier equal to 2, then after conjugacy you get 2 to the alpha. So if alpha is very small, then you are approaching a multiplier equal to 1. So somehow you get a path to connect from the hyperbolic case to the parabolic case. And when you are in the parabolic case, you can use the previous procedure. And this is the idea. Now, in order to make it work, it's a little bit hard because you have to do this in a parametric way, in a certain sense. You have to control where you are going to do this, because if you explode the neighborhood of a point, and if this point has some image, you also need to explode the image of this point. But there is a lemma if you, for instance, if you take two commutative diffeomorphisms, and if one of them has a hyperbolic periodic point, then the orbit of this point is finite. So you have to explore only finitely many points. And well, you have to deal with this, and you have to deal with the fact that there might be infinitely many hyperbolic points for which the hyperbolicity goes to 0, in a certain sense. But this can be done in a right way. So somehow what you need to do is to keep in mind this approach that I mentioned here, that what you are trying to do is to look at the logarithm of the derivative as an almost coboundary. And the idea, when you do this in this setting, is to look for Hn for which the logarithm of dHn is no longer an L1 function, but for which, when you perform this conjugacy, you are still C1. So you are looking for almost solution for the cohomological equation for which so you are looking for U such that U composed with F plus log dF minus U is close to 0 in C0 topology, but for which U is no longer a continuous function. But this is a function for which is logarithmically integrable in a certain sense, okay? And this is the right way to think about this in order to perform this construction in a parametric way. Otherwise, you will be dealing with intervals and trying to do conjugacies which are local and so on, and this becomes very technical. But if you think this way, the only thing that you need to do is to take a fine path between functions, which are no longer continuous, but which are L1.
So
yes?
when you say cohomology, is in first cohomology of discrete?
Yeah, in first cohomology. So this is so for me, this is cohomologous to this, okay? And we want to find a representative in the cohomology class which is close to 0.
Can you explain why? So I didn't follow. Why is that this cohomology condition appears? Was that related to that calculation? Or
Yes, it is related to this. Okay. Okay, essentially, this is totally related. So if you have F and you want to conjugate F and you want this to be close to a rotation in C1 topology, this is exactly the same as saying that the logarithm of the derivative is close to 0 in C0 topology. And this is because of the chain rule. This is log dH composed with F plus log dF minus log dH. So this is close to 0. Now if you call this function U, so in general you may think about this, trying to write log dF as a function of the form U minus U composed with F. Okay? And actually these two things are equivalent. And this is the right way to think in order to solve this problem where you cannot solve even in an approximate way the cohomological equation, but there are natural candidates to solve this equation, but outside the space of continuous functions. Okay? So you are enlarging your space where you find the almost solutions, and in those spaces you can take just a fine path. And this avoids doing local conjugacies and so on. So this is the way to to close the proof. Okay, and this is the outcome. So let me just remember that the space of C1 actions, not only of commuting diffeomorphism, but also of an important group on any compact one manifold is path connected. Okay, and now today I will try to move to class C2 and to discover what happens here. So the idea is trying to do exactly the same computation and see what happens, okay? So for instance, let's start with a single diffeomorphism of the circle and try to compute with these conjugacies, try to compute the second derivative. But trying to compute the second derivative is difficult because the chain rule for the second derivative is not so good, so it's better to use the affine derivative, which has a better chain rule, but as I explained yesterday, at least for C2 diffeomorphism, the affine derivative is closely related to the variation of the logarithm of the derivative. So I will keep this formula here, and this one. This one. So this is an exact formula. So I can take the variation on both sides. So I will take the variation. And the outcome is that the variation of this, well, something which is very nice with the variation is that it doesn't depend on change of coordinates. It's equal to the variation of this divided by n. Okay? And again, this is an exact formula. And if you do exactly the same computation for two commuting maps, you will get more or less the same thing. This is related to the previous computation with the chain rule and the commutativity stuff and so on. But the point is that the variation of the logarithm of the conjugate is smaller or equal than 1 over n, the variation of the logarithm of the derivative of the power. Okay? So this is very similar to what we found before with the C1 topology. Now we are in a stronger topology and we detect something which is very concrete. So let me now introduce some ingredient in order to deal with this obstruction. So everything is contained in here, and well, you know, there is this Danjois inequality that says that if you take two diffeomorphisms, then the variation of the logarithm of the decomposition is smaller or equal than the variation of the sum of the variation of the logarithm. So in particular, if you take two maps, if you take a single map and you take two different iterates, you have this inequality. And because of a classical lemma of Fekete, this means that there exists the limit as n goes to infinite of the variation of the logarithm of the derivative of f to the power n divided by n. Okay? And this is a very natural definition, and let me denote this way, v infinite of f, and let me call it this the asymptotic variation. Okay? And as I showed you before, this is the obstruction in order to perform this conjugacy trick in class almost C2. It's in class C1 plus bounded variation. Okay? The asymptotic variation. If the asymptotic variation vanishes, then we are done. This is the problem. Okay, and let me just remember that for the case of a map which is of class C1 plus absolutely continuous, you can compute the variation of the logarithm of the derivative as the integral of the absolute value of the derivative of this, which is nothing but the affine derivative. And you may think about this, about the L1 norm of the affine derivative. So this is this. So in this case, which is better than the case of the Danjois class, the asymptotic variation is the linear growth of the L1 norm of the affine derivative along the iterates. And this is the good way to think about this. Or this is my way to think about this, because this is a cocycle in the L1 space. So it is better here to think about cocycles on some Banach spaces, because in these spaces you can do affine interpolations. Otherwise, you will be dealing with some concrete dynamics and trying to perform things that may behave not so tamely, but here everything is nice. But the point is that for this you need to be in the class C1 plus absolutely continuous. And this will be important. This formula here doesn't work for the case of Danjois diffeomorphisms in the Danjois class. Okay, so let me discuss a little bit about this notion of asymptotic variation. So there are some properties. Well, because of the definition, this is a stable undertaking taking powers. So this is a formula. The variation of f to the n is equal to the variation of f times the absolute value of n. The variation of f is equal to the asymptotic variation of f is equal to the asymptotic variation of the inverse of f. This is why there is this absolute value in the first formula. The second formula is very nice, and it also follows from the definition. So this is totally general. If you have something which grows sublinearly along some action, then you can perform this stabilization procedure, and you will get something which is stable under power and which is invariant under conjugacy. This is totally general. And this is nice because this shows that this is the right dynamical version of the variation of the logarithm of the derivative. So the variation of the logarithm of the derivative is not invariant under conjugacy, but the asymptotic variation is. And actually there is a very nice formula that says that the asymptotic variation is the infimum value of the variation of the logarithm of the derivative under conjugacies. Okay? In particular, this number vanishes if and only if you can approach 0 by the you can take conjugates so that the variation of the logarithm of the derivative of the conjugates goes to 0, which means that the conjugacies make the diffeomorphism to converge in this topology to the rotation. And the conjugates you take for this realization result here are just the same that I showed before. Okay? The very same formula works. And there is a nice thing here that I will discuss maybe tomorrow, is that this asymptotic variation is a function in the space of diffeomorphisms. It is not continuous, but it is upper semi-continuous. Semi-continuity, there is a mistake there. Okay. And actually one can add some properties. For instance, again, if you think cohomologically, in case of a C1 plus absolutely continuous diffeomorphism, one can show that, if you wish, there is a kind of cohomological version of the realization statement there, which is the following. So the asymptotic variation of f equals the infimum for u in L1 of the L1 norm of the difference between the affine derivative and the coboundary associated to u, which means that u composed with f times df minus u. But here the notion of coboundary is this one. You have to multiply by this. And this is a coboundary. This is the right notion in L1 because this is a change of variables in L1. So everything is fine here. Okay, so this is exactly the same as the realization statement there. If you go into the computations. Okay, and now well, we need to do some work. We need to understand in which conditions the asymptotic variation vanishes. Okay, and here there is a first result concerning circle diffeomorphisms, and well, there is a lot of information here. So let me go step by step explaining this. So let's start with the case of diffeomorphism with irrational rotation number. We are in the class C1 plus bounded variation at least, so we have Danjois theorem. And we would like to know whether the asymptotic variation vanishes or not. And this is not a trivial issue. For instance, if you have a C2 circle diffeomorphism with irrational rotation number, then the asymptotic variation vanishes. And this is not totally obvious. And by that I mean that it doesn't follow from Danjois theorem. And the reason is that the result is false in the Danjois class. It's very surprising. The right setting for this result is this space of C1 plus absolutely continuous diffeomorphisms. Okay, so let me explain this. So let me go into the details of this. Okay, I think I will erase this. So here 2 follows from 1. No, follow from the theorem, I mean. 2, if you know that the asymptotic variation vanishes, then you know that there is this sequence of conjugates Hn for which, again, so here is the formula for the case of 2 commuting maps, but the formula for a single map was that the variation of the logarithm of the conjugates is equal to the variation of the logarithm df to the power n divided by n. So if this goes to 0, which means that the asymptotic variation vanishes, then this goes to 0, which means that this goes to the rotation in C1 plus, say, bounded variation topology, or C1 plus absolutely continuous topology, in case you are C1 plus absolutely continuous. Okay? So the key point is to know that actually B infinite vanishes. Okay? And I will give the proof of that. So proof of that the asymptotic variation vanishes for f in class C1 plus absolutely continuous, an irrational rotation number. Okay? So according to this, what you need to show is that the affine derivative can be approximated by coboundaries. Okay? If you can approximate something by coboundaries, then the growth of the cocycle along iteration will be sublinear. So this is what we need to prove. So to prove there exists a sequence of function in L1 such that when you take the coboundaries associated to this converts in L1 to the affine derivative. Okay? And the proof is by contradiction. Suppose there is no such a sequence. So, if not, then there is this magic Ham-Banach theorem that says that, well, the first thing, saying that this is not true means that the affine derivative of f doesn't belong to the closure of the space of coboundaries. The closure in L1. And in that case, Ham-Banach theorem would give a linear functional defining an L1 such that it vanishes on this space and it is non-zero here. So the first thing is that L of the affine derivative is non-zero and it vanishes on this space. That means that it is invariant under change of coordinates. Okay? Again, this is Ham-Banach. No, this is not Ham-Banach. This is the separation theorem. Is it still Ham-Banach? Okay. It's another Ham-Banach. Okay. Now, for me, Ham-Banach is the extension, no? The extension theorem of the linear function. Okay. Doesn't matter. Okay. Now, the point is that when you have a linear function in L1, it comes from integration against an L infinite function. Yes? So there exists a function in L infinite such that L of v equals to the integral. All the integrals are respect with the Lebesgue measure. And now the invariance means that the integral of u composed with f times df times this function here is equal to the integral of this for every u in L1. Okay? But now, because of a change of variables here, this is equal to the integral of u times g composed with the inverse of f. It's okay? And this equality here of this term with this term for every u in L1 means that the function is invariant. Okay? But now there is a theorem, a very nice theorem by Katok and Herman, which says that if you have a circle diffeomorphism of irrational rotation number in the Danjois class, then it is ergodic with respect to the Lebesgue measure. Okay? So here, by ergodicity with respect to the Lebesgue measure, which is not an obvious fact, okay? Because the Lebesgue measure is not, the invariant measure of the circle diffeomorphism in general is not regular. So, but it's a theorem by Katok and Herman that it is ergodic with respect to this measure. So this function is constant. And then you compute again L of the affine derivative. Well, now this is the integral of d2 df times this constant. Okay? But this is an exact integral. This is the integral of the logarithm of the derivative of f, of the derivative of this. And since we are on the circle, this vanishes. So this is the contradiction, if you wish. Because we were assuming that L was non-zero at the affine derivative of f. Is it okay? It's a very classical argument, I mean. And we use here the fact that we are in the class C1 plus absolutely continuous in order to perform this functional analytic trick. Otherwise, it doesn't work. Okay? And now, I would like to explain why it doesn't work. This is the third part here, which is really very, very interesting as well. Okay. Hélène, c'est jusqu'à quelle heure? 1h30, ok, merci. Okay, so as was mentioned by Takashi yesterday, actually, John Mather proved that many groups of diffeomorphisms are simple. So in particular, he proved that the group of diffeomorphisms of the circle in any regularity different from 2 is simple. Okay? For the case r equal to 2, this is a very difficult open question. I mean, it's a kind of nightmare. Okay. So question 1. What about diff plus C2? Nobody knows. Actually, if you ask the same question for C1 plus absolutely continuous, you get into the same troubles. This is not known whether it is simple or not. But another thing that he proved is that, in a very nice short note, is that diff 1 plus bounded variation, so the group, the Danjois group, if you wish, this is not simple. And he did it in a very explicit way. So he built a homomorphism that I will denote by M, but this is a group homomorphism from this group into R, which is actually continuous for the topology. So there is a little trick here. So this space, this is a group, and there is a natural topology here, but it is not a topological group. This is important to notice. But this is not really important for this discussion here. So there is something which is a group homomorphism which is continuous. And the point is that, yeah. Thank you. That way, no. And subjective, non-trivial. Okay. Thank you. Yeah. And if you believe that, without knowing what is the homomorphism, then you will get that the asymptotic variation doesn't vanish in that group in general. The claim is the following. The claim is that if the mother homomorphism evaluated at this homeomorphism is non-zero, then the asymptotic variation of this diffeomorphism is positive. Okay? So the counterexamples to that theorem live in this subspace where there is some singularity for for the variation. And the reason is that if the variation, asymptotic variation is equal to 0, then there exists the sequence of conjugates such that that go to the corresponding rotation in the C1 plus bounded variation topology. Okay? This is what I showed before, using these conjugacies Hn. And now, if you evaluate the matter homomorphism on this, because of the continuity, this goes to the matter homomorphism to the rotation. And something that I didn't mention, that the evaluation of the matter invariant on any diffeomorphism which is regular enough, this actually is equal to 0. Okay? Otherwise, the whole group wouldn't be simple. Okay, but this is a group homomorphism, so this is equal to n of f. Okay, and this is the end of the thing. So there is a relation between these two things. And if you wish the construction of the matter homomorphism, I will give the more or less the idea of the construction, because it's something very nice. And you will see it only lives in this subset of diffeomorphism for which the derivative is not absolutely continuous. And you will see in the definition of the matter homomorphism. So roughly, if you take an f in the Danjois class, C1 plus bounded variation, well, this means that the variation of the logarithm of the derivative is finite. So since you have a function with finite variation, you can consider the Riemann-Stiglitz integral with respect to this. So you can, for a given continuous function, you can consider the integral of this with respect to this in the Riemann-Stiglitz sense, which is a linear functional, so it is the integral with respect to a measure. So, and this measure has some decomposition. There is the regular part, the absolutely continuous part, and the singular part. So if you are absolutely continuous, if the f has absolutely continuous derivative, there is no singular part. Okay? And now you take given f, so everything here depends on f. Given f, you associate to f the integral of the, say, of the singular part of the measure. And this is m. M of f is equal to the integral with respect to the integral of the singular part of the measure. Okay? And it behaves as a group homomorphism. So if you do the chain rule, and you see, it is a group homomorphism. Okay, and this is the definition. This is a very nice construction that shows that that question of simplicity of diff2 of the circle is delicate. Okay. Okay, so 10 minutes. Okay. Yes?
What goes wrong if you also consider the absolutely continuous part?
No, there is nothing is wrong. Nothing is wrong. So you will get the same, actually. or minus the other one. But the point is that when the singular part disappears and you integrate only the absolutely continuous part, you will get 0 because you are integrating an exact derivative. Yeah. This is the point. Yeah. So I remember when I read the paper of Mather, I asked to me the very same question. What is wrong with taking this? It's the same. the total integral equals to 0. So this is a measure with a sign, I mean. Okay. Okay. So we have good news for the case of the circle. By the way, this is one of the reasons why we are not able. Yes. you had to do the chain rule, and you had to look at the change of the measures under the chain rule, and
It's easy to understand the singular part of the composition and so on.
yes. This is why I put this here, the construction up to some details.
Actually, there should be more homomorphisms than just this one.
This is a question. Maybe you know, Takachi. Is the kernel of the mother homomorphism a simple group?
No, sorry.
Yes.
Sorry, actually, you can take another homomorphism instead of singular part. You consider only atoms, only discontinuities, and it will be another homomorphism.
No. But I am in C1. Okay, I think so. In that case, you are in a piecewise C1 case.
Yeah.
Maybe.
I still want to say no, but we should keep it to the question.
I don't know, but so I also have some questions on that. So actually, this is the reason why we are not able to prove that the space of commutative diffeomorphism in the Danjois class is connected or path connected because of this. We really need to have a vanishing of the asymptotic variation, and we don't have in general vanishing of the asymptotic variation in the Danjois class. But I think this is still doable. Okay. There is another step in our proof where things become more delicate. But I agree with you. I think this is interesting to concentrate on the kernel of this homomorphism. And now let me discuss a little bit in these 5 minutes in order to explain what I will do tomorrow is the case of the interval, which is essentially the case of where you see some periodic points or fixed points. So essentially, we are reduced to the case where we have a diffeomorphism with no fixed point in interior. Otherwise, you can decompose your manifold into pieces where you see no fixed point in interior. And we will assume that the endpoints are parabolic. Otherwise, we already had an abstraction with the hyperbolicity. But we already knew how to kill this abstraction by composing with these continuous maps that are not differentiable. So let me concentrate on something very concrete. So diffeomorphism in the class D, which are very boring from the point of view of dynamics. So they point everything to the right or to the left. Okay. And so there is no fixed point inside, and we will assume that the endpoints are parabolic fixed points. And the naive conjecture is that, again, the asymptotic variation vanishes if you are regular enough. Okay? But it turns out that the answer is no. And the answer is generically no. Okay? And this is what I will explain tomorrow. There is an obstruction, and there is a deep obstruction to having vanishing of the asymptotic variation, okay? And the obstruction comes from another construction of John Mather, which can be reinterpreted.
It's just you put M to very different things.
Yeah, but this is M and this is M of F. Well, it's the same matter. I mean, what to do? J for John, I don't know. This is the Mather invariant. And it turns out that the asymptotic variation is closely related to the Mather invariant of a diffeomorphism. So let me recall very quickly what is the Mather invariant. So, and then I will come back to this slide. So when you have a diffeomorphism of the interval of this way, with no fixed point in the interior, as I claimed yesterday, there is a vector field on the left and a vector field on the right, which are the Ezequier's vector field. And in general, they do not coincide. And the Mather invariant measures this default of coincidence. So you can, using the vector field on the left, you can parameterize F you can parameterize the interval as the real line so that f becomes, after change of coordinates, the translation by 1. And the same on the right. And then you have the change of coordinates. And the change of coordinates is just a diffeomorphism of the real line of the same regularity class of f that commutes with the translation by 1. But it is a diffeomorphism. It is not necessarily a translation. And this is the mother invariant of f. Except for one thing, is that when you do this identification, you are choosing a base point on the left and on the right, which means that actually this m here, okay, I agree, this is not a good notation, this is another m. This m here, this is a diffeomorphism, but which is not canonically associated to f, because it depends on the choice of 2 base points. So you have to compose on the right and on the left by rotations. And the class of this diffeomorphism is the mother invariant. And it is an invariant because it is an invariant under conjugacy, and it captures a lot of information about f. And the information we are able to relate is this one. So the asymptotic variation of f is equal to the variation of the logarithm of the derivative of the mother invariant. The mother invariant, you can see it as a circle diffeomorphism up to composing with a rotation on the right and on the left. So the variation of the logarithm of the derivative is well defined, because if you compose on the right or on the left, you don't change the variation of the logarithm. And this formula says that the variation will vanish if and only if the mother invariant is a rotation, which means that the coordinates on the left and on the right are the same, which means that the 2 vector fields are the same. Okay? And this is not at all the generic case. The generic case is when these 2 vector fields are different. Okay? But it turns out that this is what I claimed yesterday. This is the key point in order to solve the question. If the mother invariant is non-trivial, which is the difficult case to deal with, because in that case the asymptotic variation is positive and we cannot play this game of conjugating, there is a theorem of John Madden, which is not difficult at all, that says that the centralizer is infinite cyclic. So in that case, instead of dealing with 2 commuting maps, we are dealing with 2 commuting maps, but these 2 maps are powers of a same diffeomorphism. And in order to deform the action, we just need to deform the generator. Okay? So we are somehow in a good situation. We can deform this generator just by moving the graph through a linear isotopy to the diagonal. Okay, and this is the strategy. But the point is that there are many technical issues here. There are at least 2 technical issues. I will explain that tomorrow. So thank you very much.